where a single eigenvalue can have an eigenspace of dimension 2. Most often, we might see that a single eigenvalue, it has an eigenspace of dimension 1, but there are special cases where a single eigenvalue can have an eigenspace of dimension 2, because the null space of A minus lambda I of a specific lambda can have nullity equal to 2. So when we talk about the eigenspace is a function of each lambda I. Okay, so if we have a matrix A minus lambda I times I, this is the identity matrix. The times x, if this is equal to 0, here the nullity of the matrix A, let me give it like this: minus lambda 1 I is some number, and then you have to discuss about the nullity of A minus lambda 2I. Okay, this is another number. So I'm just writing this one explicitly this way because sometimes we forget that that we are going to discuss about the eigenspace of specific eigenvalues. Okay, so the nullity is the dimension of the null space. So this is the dimension of the eigenspace of lambda 1. So let me explicitly write it like this. So this is the dimension of the eigenspace of lambda 2. Okay, so yeah, let's move on. So we discussed these, and we care a lot because in the A, and by the way, when we talk about the diagonalization using, because we can diagonalize the, so let me write it like this: the diagonalization using eigenvalues, this is possible only for these types of matrices. Okay, and for which are square, and for this one we need n eigenvectors. Okay, so we need n eigenvectors, and then we talked about the algebraic multiplicity, and for the wait a second, the algebraic multiplicity, the geometric multiplicity, and today we want to talk about the applications of diagonalization. So the major schema which I often want to use is the following. So here we have the standard basis. We're doing diagonalization. So if we have any matrix A in the new basis, let me call this one made of eigenvalues, this A is going to be a diagonal matrix. And then here, any vector here x0, okay, this has another vector here which we can denote this as u0 in this new domain. Okay, we're talking about the same vector. But what happens is that if these vectors, if this vector x0, let's think for a moment, if this is equal to is a function of time. Okay, so if we have here x0 is x of time, a function of time, which means that this can generate, which means also that we have also x1, we have a vector x4, etc. These are vectors. Let's not forget that AU is a matrix. Then similarly, the u0, let's assume that this is also a function of time. But now, if these are all vectors, we should not forget that we can transform from one domain to the other using a matrix P. What is the matrix P made of? The matrix P is composed of the eigenvectors, each having a single column, eigenvector v1, v2, and vn. So, so it looks like we can use this matrix P to move this way, and then, so this means that x at any time, this can be written as a matrix P This is a matrix P times a matrix a vector U0. So if we want to solve a problem which is developing as a function of time, it would always be very useful to solve the problem here with a given input, because sometimes whenever we solve the problem, we have some given input which might be defined in this domain. We transfer the problem here, we solve, and we obtain all the necessary solutions, and we can always come back. Okay, come back, which means that we can describe the problem how it looks like in here. Now, before we initially we want to let me start in this way. So this is how we transform a vector. What about the matrix? How do we diagonalize a matrix? The diagonalization of a matrix is always written as P inverse times A times P. Okay. Then from here we can multiply from both sides of the equation with a matrix P. We can say PD is equal to P inverse AP. So here we get PD. This is equal to AP because P times P inverse. This is equal to the identity matrix. Okay. Then we have PD is equal to AP. Then if we multiply from by P inverse, if we get PD P inverse, this would be equal to matrix A. So it looks like from this relation, we also can obtain the following. So the matrix P, which is composed of the eigenvectors of matrix A, so let's not forget this, can be used to write D as a function of A, but at the same time A as a function of T. Now, one thing that we can find useful, the use of the diagonalized version of the matrix, is the following. Let's assume we want to find A squared. If this is A squared, we can write this one as PD P inverse, PD P inverse times PD P inverse. Okay, so we are using this expression here. And then we know that when we multiply two matrices, we can pair them up whichever way we want. So if we multiply these two together, P inverse times P, this would be equal to P D squared P inverse. Okay, so this is what we get. So similarly, as you can see from here, because this is the identity matrix, so this is like gone, D times D. So what we can do is that we first multiply these two, which is the identity matrix, and then we can multiply D with D. Okay, all from this we get D squared. So similarly, we can write that A to the power 3, this is equal to P D to the power 3 P inverse. Okay. Then I think we can also write down that P A to the power n is equal to P D to the power n P inverse. So it looks like, so now what would be the use here? The thing is that the calculation with matrices, it might be computationally expensive, which means that we have to do a lot of additions, multiplication, and subtractions whenever we multiply a matrix which can be 3 by 3. So for example, if we want to calculate the A, and to find the A squared, we have a 2 by 2 matrix, and then we have to multiply 4 numbers, which will appear around here, and this will give A squared, let's say so. But if we have a diagonal matrix and we want to take the square of that one, let's assume that the eigenvalues are 1, 2, 0, 2, and this will simply be equal to 1 squared, 0, 2 squared. Okay? So this would be the square of a diagonal matrix, and this one is much easier than multiplying the first row with the first column. How many calculations do we have here? We have 2 multiplications plus 1 addition. That's 3 calculations, okay? Then we multiply the first row with the first column. Here we have again two multiplications, 1 addition plus 3. So it looks like in principle this is 3 plus 3 plus 3. So here we have a total of 12 operations, okay, 12 steps. And if we have a matrix which is n by n, so assume for a moment we have the multiplication of an A, which is n by n, and we want to find the square of A, or let's assume that we can also multiply a matrix A by matrix B. Then what is the number of calculations? You can all calculate this one on your own. But let's think for a moment that if this is a n by n, we're going to get a matrix which is b n by n also. And assume for a moment, in order to get the b11, how many calculations do we need to do for the b11? We have to multiply the first. Yes, say it.
3. I mean, we have 2 multiplication and 1 addition. In
no,
this case,
matrix is n by n. The matrix is not 2 by 2. So this is n numbers and n, okay? So to obtain b11, how many calculations do we need? We have to do the following. a11 times b, because when we multiply two matrices, how is the multiplication defined? So let's do it like this. Cij, this is equal to aij times, no, this is ik times bkj, okay? So this means that the k, it will be a parameter which is going to change. So we are summing here k from 1 to n, and this will be aik bjk. So this means that if we're going from 1 to n to get each number, how many multiplications do we have? K, here we have n values, right? So we have n multiplications. So we have n multiplications. And we have also n minus 1 additions. Would you agree? Because let's multiply, let's give an example. So here we have a matrix which is 1, 2, 3, 4, minus 1, minus 2, 0, 5, 1, minus 1, 3, 4, 1, 2, 3, 7. Okay, let's assume that we want to multiply this one with another matrix which is minus 1, 2, minus 3, 4, 5, minus 1, 3, minus 2, 1, minus 1, 2, 0, 3, 4, 1, 7. So let's assume that we want to multiply these two matrices. And how? So let's use this formula. Let's say that we want to find what is element C. You pick one. What number do you want to calculate? C334. Let's do this. Do you agree? So if we're going to find the C34, which this means that we have to multiply the third row of this matrix, okay, with the fourth column of this matrix. Okay? Then how do we do it? It looks like this will be equal to, based on the definition here, this will be
4 multiplications, 3 additions.
That's true. A3k times b k4, okay? But then k is from 1 to n. So this is equal to, let's think for a moment, if k is equal to 1, k is equal to 1, what do you observe? We have A31 times B14, right? Then for k equal to 2, we have A32, B24, k is equal to 3, A33, B34, and k equal to 4, A34, B44. Is it correct? Looks like it does. Okay. So what we are saying here is something we know. 1 times 4, minus 1 times minus 2, 3 times 0, 4 times 7. So this is, we have to add all of these. So we have 4 multiplication and 3 additions. So this is what we get. So for one operation, how many do we have? It looks like we have n plus n minus 1. Okay, this is how many calculations we have for one number. Okay, and but how many numbers do we have as a result? Η matrice është 4 me 4. Sa element ka? 16.
16.
So it's n squared. So this is for single element. So this number is a single element. But if we want to calculate the square matrix, then we have to multiply this with n squared. So here we have n squared times n. So this n plus n minus 1, we can write this one as 2n minus 1. Okay? So the total number of calculation is 2n cubed minus n squared. 2n cubed minus n squared. So it looks like the number of calculations, it increases with n. So n cubed, it's a polynomial increase. It's not bad. Computers can easily solve problems that have polynomial complexity. The problem is when we have an exponential complexity, where the number of calculations increases exponentially. But this one is fine. But anyway, this is a lot of calculations when we compare it with simply dealing with the diagonal term. Okay, so this is how we can calculate the number of steps we need to do. But then it looks like we can argue a little longer and reporting the same thing, that diagonalizing a matrix, and if we have polynomials which include matrices, this could be a good choice or a good reformulation. Now, this is how we deal with the powers of a matrix. Then, so we can make use of this one in this way. Now here, we use this section only to clarify how we do the calculations of a specific matrix. Now, another problem that we can solve using the matrix notation is to find how a function changes as a function of time. Now, to see how a function changes as a function of time, we can define, let's see for a moment. So, this is the original problem. So, this is the part on the board which can stay a little longer. Or let me write it like this. So, we can have a problem which can be defined as follows. We can say that any x at a subsequent instance, this can be described as a matrix A times xt. Okay, so this is a vector, and this can also be. You can also think this one as if it's not a vector, just a single entry. So this means that there is a relationship between any two subsequent values, which are A, xt. Okay, so what this means is that if we are given x for t equal to 0, we might be given x0. But for t equal to 1, then x1 will be equal to ax0. And this x0 can be equal to, let's assume for a moment, a can be equal to 2. Okay, and let's see, we are discussing the moment where x is not a vector, then this would be, and let x0 be equal to 3. So what we see here is that x1 is equal to a times x0. Then for t equal to 2, we find that x2 is equal to a times x1. But this is also equal to a times x0. So we get a squared times x0, right? So for t equal to 3, we can say that x3 will, similar to this, we can simply write that this is a3 times x0. And the t equal to 5, the x5 will be equal to a5 times x0. So let's substitute a couple of values. We have a times x3, this is equal to 6. Then here we have a squared, which is 4 times 3, this is equal to 12. And similarly, this is 8 times 3, this is 24. And here we get a to the power 5, this is 8, 16, 32 times 3. Okay, so these are some values where x is not a vector. But let's assume this is a vector, and the situation will configure like this in here. And then we can, wait a second, so, yeah. Now, maybe it's best if we cover an example. So let's see this example. Assume that let's assume that we have a variable xt plus 1, which is equal to 7xt minus 15 yt. And yt depends on the previous coordinates or the previous values of x and y as such. Okay? So assume that this x and y, this can be a pair of numbers which might define a system or some specific values, but apparently they are changing recursively, okay, depending on the previous values. So now this system, we call this one difference equations. So this is a system of difference equations, and we want, so probably it's best if we think about this one as if this is the path of a particle, because we're used to x and y. So let's assume that we start at the point 1, 1. So we're at point 1, and this is another point 1. So it looks like we are here at the first moment that we do the measurement. But then where are we going to be after this moment? Then let's see what will be x. This is x0. This is x0. We start, well, let's give this here. Given that x0, y0, it's equal to 1, 1. And then we want to find what is x1. x1, then it's going to be 7 times 1 minus 15 times 1. So this is 7 minus 15. This is equal to minus 8. Then y1 is equal to 2 minus 4. This is equal to minus 2. Okay, we found minus 8 minus 2. Minus 8 is going to be somewhere here. Minus 2, it's here. So apparently, from here we jump to here. Then what is x2? x2 is equal to 7 times minus 8 is minus 56. Plus 30 minus 26. This is minus 26. What is y2? y2 is 2 times minus 8 minus 16 plus 8 minus 8. Minus 8. So it looks like from this point we move a little further. So it looks like we're going to move somewhere here. So this is we find that, so this is y2, x2, y2, then we need to find x3, y3, and so on. So it's like a system that is developing over time. And then the question is, how can we try to solve this system? Now, it looks like, given the example that we saw here, we have here, what can be very useful is to write, so we said here x, this is equal to a times xt. We can simply write this one as this is a to the power t plus 1 times x0. Okay, so this is the matrix which we raise it to a specific power, and we multiply it with the x0, so we can find what is the pair of numbers, or what is the vector at some times later. So for this system, so if we can use diagonalization, well, let's first try to define the problem a little differently. So this xt plus 1 and yt plus 1, this is equal to 7 minus 15, 2 and minus 4 times xt yt. So this is our problem, which is defined as any vector x t plus 1. This is equal to a 2 by 2 matrix times this vector x. Okay, so this is how we pose the problem. Apparently, we know what A, we find out what is A, and the moment we find out what is A, we try to diagonalize it, and the relevant matrices that we're going to work with are these. A, I think A is given. Maybe we don't need to write this again, because it is explicitly here. Then we need to find the diagonal matrix. The diagonal matrix here, D, this is equal to 1, 2. okay, because the eigenvalues of this matrix A are 1 and 2. We have solved this one before, but let's give the answer here right away. Then we have the matrix which is composed of the eigenvector of 1 and eigenvector 2. The matrix P, it looks like 5, 2, 3, 1. This is 5, 2, 3, 1. Then we need also the matrix P inverse. The matrix P inverse, it can be written as P inverse, it's equal to minus 1 minus 5. Wait a second. 5, 2, 3, 1. This is minus 1 minus 5. And we have 2 and 3. Okay, so this is what we obtained here. And then the question is, let's try to figure out what is a to the power n. So this a to the power n, this is the major question. And this is equal to p times d to the power n times p inverse. And p itself is equal to 5, 2, 3, 1. D to the power n, it is 1 to the power n, it's always 1, 0, 0, 2 to the power n, multiplied by p inverse, which is minus 1, 3, 2, minus 5, okay? So this is a to the power n, and here, let's try to multiply these two matrices first. So this is equal, this is equal. So here we have 5, let's multiply the first row here with the first column. So here what we obtain is that we get here just 5, okay? Then we can multiply the first row with the second column, which
3
is,
times 2n.
that's correct, 3 times 2 to the power n, that's it. And then we multiply the second row with the first column, we get simply 2. And then we multiply the second row with the second column, we get here just 2 to the power n. So this is multiplied minus 1, 3, 2, minus 5. Then again, what we obtain is that 5 times minus 1, this is minus 5. Then what is this?
6 times 2 to the power n.
Yeah, that's true. Then we have 5 times 3, this is 15, minus 15 times 2 to the power n. Okay, then we multiply, we get here 2, this is minus 2. So we multiply this here with this column, so we get minus 2 plus 2 to the power n. And then we have
6 minus 5 times 2 to the power n.
Is it 6? 6 minus 5 is 2 to the power n. That's true. Okay, 2 to the power n. Okay, so if this is a to the power n, this is what we are looking for. This is a to the power n. So we can write this one simply like this. Okay, we found a to the power n. The a, it was diagonalizable, so it was easy for us to move forward with this. And then let's see what is xt, okay, or xn. Let's consider this one. What is the vector xn? So this is going to be equal to the same matrix, which we can write this one minus 5 plus 6 times 2 to the power n, 15 minus 15, 2 to the power n, minus 2 plus 2 to the power n, 6 minus 5, 2 to the power n, times x0. x0, it is 1, 1. So we want to find, so we start with this 1, 1, and then we are going to get a vector as a function of n alone. So if we multiply here the first row with a single column, so okay, and again, sometimes students might find this useful. So this matrix, this is 2 by 2, and this vector is 2 by 1. So we expect a vector which is 2 by 1, just two numbers, a pair of numbers, which can be considered as a coordinate since we are using the notation of x and y, only for that. So then, let's see what we get. This is 15 minus 5, this is 10, this is a constant number, and 10 and
minus 9.
minus 9 times 2 to the power n. Okay, and then the other number we get 4
minus 3.
minus 3 to the power n. Minus 3 times 2 to the power n. Okay, so this is the new coordinate x at each moment late, well, at each subsequent instance. So here we can see that finally this little x of t, this is equal to 10 minus 9 times 2 to the power n, and y of t, this is equal to 4 minus 3 2 to the power n. So now it looks like initially it looks like a very good solution, because now later on in time the x and y, they are not coupled. Okay, so this is also very important. So if you look at this expression here, it is an important keyword which we can write it here. So the system initially, it is coupled. And having coupled systems, now the variables are coupled together. We don't like them. We don't like the variables to be coupled too much, because interdependency might make the problem difficult. That is one of the major reasons why we diagonalize systems, because if we diagonalize the systems, then we have these off-diagonal terms. They are all 0, which is something good, because x later in time will depend only on the x much earlier. Okay, so here we have, so here it looks like we found a solution, and the variables, or the two coordinates now, they are like this. They are decoupled. Okay, so this is something very, very important, or something very useful that comes out of this element, or of this diagonalization issue. Do you have any questions regarding this? Okay. If you have no question, we can have a short break.